I thought I'd break this up into a couple parts. It seems pretty long, so here we go. Introducing enthalpy. So the difficulty is that most chemical reactions don't have any measurable work. So how do we deal with that? So we talk about something called enthalpy, and it's in terms of heat only. Heat is the only thing that we have. So in doing so, we get this new symbol H. But we're only really concerned with change in enthalpy, or delta H, from a chemical reaction. Okay? So if we look at this graph, which we've kind of seen something like this before, we can see that we have the reactants up here, right? We have the products down here. Let me find the products, right? And we can see the delta H because the reactants are higher than the products. In terms of energy, it's going to give us something negative because we've got a smaller number minus a bigger number. And we can see that this is going to be exothermic. Okay? But that is exactly what enthalpy is. Enthalpy is the energy of the products minus the energy of the reactions, and it's always going to be. We will look at it in different forms, in different ways, but it's always going to be products minus reactants, no matter what you do, no matter what you say. Almost all of these functions that we'll talk about in this unit are going to be products minus reactants. Okay? Sorry, I just bumped the speaker there. So, delta H is called a state function. That means that it doesn't matter which pathway it takes. And you're going to find that when we start talking about Hess's law, when we take different pathways to get to the same result, and it's always going to be the same number. And that's what it means to be a state function. Almost all thermodynamic functions are state functions. Okay? Delta H is equal to Q at constant pressure. So all those calorimetry things that we're going to be talking about in just a minute, the Q that you calculated was equal to delta H because we had constant pressure going on. It was the atmospheric pressure. That did not change over time. Okay? Enthalpy can be calculated from several sources though. We can use stoichiometry to calculate it if we're given some values. If we're given delta H values for a reaction, we can calculate the enthalpy of a certain amount. We can use calorimetry. We can use a table of standards. We can use Hess's law, which sometimes uses a table of standards. And we can use bond energies. And we will be using all of these in this unit. We're starting out with the first two. The other ones we'll leave for a little bit later. So, a reminder, the enthalpy is the way that we measure transfers of heat in a chemical reaction. So in a chemical reaction, we measure enthalpy by looking at transfers of heat in a chemical process or reaction. And yeah, I said process for real because some things that we talked about, like dissolution, that's not a reaction, that's a process. So enthalpy of reaction, that's delta H RXN. That includes the reactions like neutralization, delta H NEUT. Or combustion, delta H of COMB. Both of these are just specific types of reactions and they're given their own little symbol, but notice it's still delta H. It's still the enthalpy change, so that means it's the products minus the reactants, always. Okay? So the enthalpy of formation, that means bond forming. So how much enthalpy, how much energy does it take for the bond to form? Enthalpy of fusion, how much energy does it take for a substance to melt or freeze? Remember, that's at the same point. Freezing happens at the same point that melting occurs. And then finally, vaporization. Vaporization is for a substance to turn into a gas or opposite, to condense into a liquid. So when we're talking about those points, those are specific to physical processes. So this one, and another one that we call delta H of dissolution, right? These are all physical processes. These up here are all chemical processes. So I said processes for a reason because I want to make sure that you understand we can find delta H of physical and chemical processes. Okay, so enthalpy values are always, for us, from now on, going to be expressed in kilojoules per mole of reaction. I know it says kilojoules per mole in one because you see that a lot in the AP exam, but that means kilojoules per mole of reaction. or mole of whatever substance it is. But some of the older printed materials that were before the revision happened may just say kilojoules or joules. So be really careful about that because they're saying the same things. Okay? Standard conditions. So you guys already know about STP. But if you recall, the temperature at STP is 0 degrees Celsius. And I don't know about you, but I've been sitting at 0 degrees Celsius for several days now, and I am cold. And I would not be happy if I had to be in a lab that was as cold as it's been this afternoon. That would not make me happy to have to be there. I would be a frozen popsicle and I would stop doing my job very quickly. So when I think of standard conditions, I think of conditions in which I'm going to be much more comfortable. So that's 1 atmosphere of pressure, which usually doesn't change too much, and 25 degrees Celsius. Now that's really important because 25 degrees Celsius is around 75 to 80 degrees Fahrenheit, which is really comfortable for us. And if solutions are involved, they have a concentration of 1 molar. Okay? All of this information is communicated by adding this little, looks like a degree symbol to all of the state functions. That's Gibbs free energy, that's enthalpy, and that's entropy. And we'll be talking about G and S a little bit later. So if you see delta H naught, that thing is usually said as naught. That's N-A-U-G-H-T, naught. It's an old word that meant 0, okay? Then you automatically know what the pressure and the temperature, and if you have a solution, any other conditions that would be standard conditions. That's really important. And this is where every year I have to look up the difference between STP and standard conditions because they're very similar, but they're different. So now you know why I had that problem when I was talking about gas laws. Okay? So exercise 4. Here we go. So upon adding solid potassium hydroxide pellets to water, the following reaction takes place. And this is a dissolution process. So this is one of those physical processes that happen that we can find the heat of. So we have potassium hydroxide that results in, when dissolved in water, results in potassium ions that are aqueous and hydroxide ions that are aqueous. And look over here, 43 kilojoules per mole of energy. Notice where that is. It is on the product side. And we learned just a little while ago that if it's on the product side, that means the reaction is exothermic, which means that's a negative change in energy. Okay, that's going to be really important for us later on as we define things. Answer the following questions regarding the addition of 14 grams of KOH to water. So this is 1 mole of KOH. Now KOH is somewhere about 56 grams per mole. So 14 grams is certainly not a mole. How much energy, though, is 14 grams? Well, we can figure that out. So the questions that were asked first is, does the beaker get warmer or colder? Well, the beaker gets warmer. How do we know that? Because the energy is on the product side, which means it's exothermic. It's giving off heat. Is the reaction endo or exothermic? Well, it's exothermic because it's giving off heat. Okay? What is the enthalpy change for the dissolution of this substance? So let's look at that. I know it's 14 grams. I know that negative 43 kilojoules per mole is what I need. So what do? Stoichiometrically, I start out with 14.0 grams of KOH. And I change that to moles of KOH by using 56.08 grams of KOH per 1 mole of KOH. Okay, and then I use the negative 43 kilojoules per mole of reaction over 1 mole of KOH. You gotta be really careful of this because this is really moles of the reaction, moles of the process. It is not moles of KOH. So moles of KOH cancel out, grams of KOH cancel out, and we end up getting negative 10.7 kilojoules per mole of the reaction, and that would be the answer. So we use a little stoichiometry here, and then we had the addition of some information that we were given in the reaction that's going to help us understand what's going on. Okay, yes, this looks a little bit sloppy and a little bit crazy right up here in this moles of KOH, but remember, 1 mole of KOH gives me negative 43 kilojoules per mole of reaction. So that's where we come up. That's where that comes out. So calorimetry. So we've just talked about stoichiometry. Stoichiometry is always going to be stoichiometry. It's going to be the same. Grams to moles. Information from moles to something else. So as you can see, we're going to use stoichiometry all the time. So the process of measuring heat based upon observing the temperature change is called calorimetry. So when something absorbs heat or energy or discharges heat or energy, we can measure the temperature difference between two substances doing that. And that is a process called calorimetry. Coffee cup calorimetry is very specific though. This is how we find the energy of a particular system. Because we have styrofoam cups, we can actually look at two different things and find the change in temperature. So we have two different cups. The cups are nested inside one another to help us get a thermal barrier. We add something inside the cup. We add something to that cup. We stir it and measure the temperature. That's what we do. We're looking for change in temperature. So after the data is collected, we can use mass or volume and initial and final temperatures, and we can find the energy released or absorbed. Remember, Q is equal to M times C times delta T. Remember that C is the specific heat. There is also molar heat capacity. And if you have molar heat capacity, what does that mean? It's the heat capacity per mole, or it's heat capacity per mole, okay? So we refer to this process as constant pressure calorimetry, and in constant pressure calorimetry, Q is equal to delta H. So all of those problems that you solved for from last week, Q gives you delta H because of the conditions that we're at. They're constant pressure conditions, so therefore that holds true. So here we go. Here's exercise 5. In a coffee cup calorimeter, 100 milliliters of 1 molar NaOH and 100 milliliters of 1 molar HCl are mixed. Both solutions were originally at 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius. Assuming that all solutions have a density of 1 gram per centimeter cubed, that's going to be really important, and specific heat capacity of 4.184. Now notice, these two values are of pure water. But neither one of these solutions are really pure substance. They're mostly water. So when we have solutions, we are going to assume conditions of water, almost always. So even if it's not given to you, if you have solutions that are 1 molar or less, we assume conditions of water. 1 gram in density, 4.184 kilojoules per mole. Calculate the enthalpy change for the neutralization of HCl by NaOH. Assume that no heat is lost to the surroundings or the calorimeter. So we know that delta H is equal to Q. And we know that Q is equal to M times C times delta T. So here we go. We know we have 100 milliliters of this and 100 milliliters of that. Add those together and we get 200 milliliters, but 1 gram per milliliter. So that means that we have 200 grams of the substance. Now, these solutions were originally at 24.6 and 31.3, so they increased in temperature, which means that everything is being given off. So we're going to make that negative. Everything is going to be negative because we have an exothermic reaction going on here. So we know in the end we have to have a negative sign in there. We have heat capacity is 4.184 joules per gram degree Celsius. So I'm sorry, I'm getting ahead of myself. Times the change in temperature, 31.3 degrees Celsius minus 24.6 degrees Celsius. And we do a little bit of magical calculation, and we end up getting, I'm looking at exercise 5, we end up getting 5,600, negative 5,600 joules, or negative 5.6 kilojoules per mole. How do I know per mole? Well, I have 1 molar of each of them. If I know anything about this reaction, I have H plus OH minus yielding H2O, and you will notice it's 1 mole of each of them. So everything I do is going to be 1 molar. So I get negative 5.6 kilojoules, and I can say per mole because I have 1 mole of each of the things reacting. Okay? Equal molar volumes. Okay? All right. Problem 6. When 1 mole of methane is burned at constant pressure, 800 kilojoules of mole of energy is released as heat. Calculate the delta H for the process in which 5.8 gram sample of methane is burned. So we know that methane plus O2 yields CO2 plus H2O plus 890 kilojoules per mole of energy. That's heat released, okay? So this is assuming 1 mole of this. Now that means there are more moles of oxygen, but I'm not really worried about the oxygen. And in the end, I have 2 of these, which means I have 2 of these. But really what I'm looking at is 1 to 1 right here. Okay, I'm not really worried about the 2's and the 2's. I'm not looking at, if I were looking at oxygen, it'd be a little bit of a different situation, but I'm not. Okay, so 5.8 grams of methane. I'm going to switch that straight to moles. Okay, so that would be 16.042 grams of methane over 1 mole of methane. And there's 1 mole of methane to negative 890 kilojoules per mole of reaction. Okay, why did I make it negative? That's on the product side. It's exothermic, which means the sign of delta H is negative, or the sign of Q is negative. So I go through and I figure this all out, and I get negative 320 kilojoules per mole are released, or negative 320 kilojoules. Okay, so pretty simple. So let's look at problem number 7. Gets a little more complicated, but not so bad. When 1 liter of 1 molar barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of 1 molar sodium sulfate solution at 25 degrees Celsius in a calorimeter, a white solid forms, and the temperature of the mixture increases to 28.1. So once again, I'm increasing in temperature. I'm giving off heat to the surroundings, which means I'm going to be negative. So I got to remember that. Assuming that the calorimeter absorbs only negligible quantity of heat and the specific heat capacity of the solution is 4.18, remember, there's water. And the density of the final solution is 1 gram per milliliter. Again, water is assumed here. Calculate the enthalpy change per mole of barium sulfate formed. So the first thing I need to do is I need to go, okay, hang on. Barium plus sulfate, these are aqueous solutions, yield barium sulfate solid. I can see 1 mole, 1 mole, 1 mole. And if I remember, I had 1 liter of a 1.0 molar solution, which means I had 1 mole of that substance. So that's all good stuff right there. That makes really good sense. So we go delta H is equal to Q, which is equal to M times C times delta T. So M, remember, I had 1 liter of barium and I had 1 liter of the sodium sulfate solution. But I want everything in milliliters because I have grams per milliliter and I want grams, okay? So 1 liter is 1,000 milliliters, so I have 2,000 grams. Okay, I'm going to make everything negative because I know it's got to be exothermic, times 4.18 joules per gram degrees Celsius. And the temperature change was 28.1 minus 25 degrees Celsius, Okay, so we end up getting negative 25,900 joules per mole. But if we change that to kilojoules, we get negative 25.9 kilojoules per mole, mole of reaction. Okay? So we didn't have to do too much of anything to get that, except to understand that we had 1 mole of this and 1 mole of this to 1 mole of this, and everything came out to be just fine. Okay? So that will be the end of part 1 of notes. Sorry it took so long to get that done.